Sham, and in this video uh, I will be analyzing audio signal and then filtering out the noise using FPGA. I'll start the project and explain everything and give you the whole process end to end, so stay with me. So I'll start from reading my audio signal. So that's how my audio signal looks like. Okay, so this is my audio signal. Audio signal is 7 seconds long, and it has a noise of 1 kilohertz and 5 kilohertz apart from the frequencies of my sound saying arsh 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 arsh. Okay, let me play this video, let me play this audio for you sound, and it's my audio is recorded in X variable, and then this arsh 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 arsh. So yes, as you can see, it's my audio of so yes, so our goal is to remove this noise of 1 kilohertz and 5 kilohertz, this key noise. So how we are trying to do is, like, I have used the filter designer app to design the band stop filters for 1 kilohertz and 5 kilohertz, and I've got the coefficient numerators N1D1 and N2D2, each for 1 kilohertz and 5 kilohertz respectively. And then what I'm going to do, I'm going to convolute these numerators and denominators, and then I'm going to get uh, a cascaded numerator and denominator which will act as a filter for both the frequencies. So yes, so as we let's go step by step. That is for filter number 1, and then our space is populated with N1D1 and 2D2 and then convolution, and then this is the frequency response of our band stop filter for 1 kilohertz and 5 kilohertz. If you see that the band stop filter is arranged in such a way that it will attenuate the frequencies specific to 1 kilohertz and 5 kilohertz, since my audio is way below 1 kilohertz and 5 kilohertz and it is spread across the spectrum. So removing 1 kilohertz and 5 kilohertz precisely will not affect my original idea, original audio. That's the whole idea. And so VPA value precision, so I mean, since num and then our floating point, double floating point numbers. So let us see what they represent in value precision arithmetic. So these numbers are pretty long, and this is, but let's see the response. I'll come back to later how about the quantization part. As of now, let's see how the processed filtered audio will look like. So YF, yes, YF is the signal of the filtered audio. And okay, so I've made another function called spec. So what does the spec do? Is spec will help us analyze that signal. So yes, after after the signal has passed through the filter, you can see that there's no component of 1 kilohertz and 5 kilohertz. And yep, let's hear the sound of the filtered signal, which was YF. Arsh, 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 arsh. Yep. So with that being said, let us quantize the coefficients because it serves the purpose, but our goal is to implement this algorithm into FPGA. But before moving to the hardware, we want to make our signal processing algorithm, which is the filter. In this case, we want it to be computationally not that intensive. So our goal is to make it fixed type, and also whenever we want to create any yes, so yes, we want to quantize the coefficients also, and we want to make the coefficients fixed point because that's a prerequisite when we are converting a continuous time domain filter to a discrete time domain. Sorry, when we convert a signal processing filter from continuous to discrete, we need to make the coefficients fixed point. So with that being said, let's quantize these coefficients. The way we do it is, okay, we'll analyze that frequency response later, but how we do it, we fix the coefficients with 16 digits word length and 12 bits, sorry, 16 bits word length, and out of those 16-bit word length, 12 bits are reserved for the fractional part, and one just signifies that the coefficients can be signed or unsigned, and that's the way to convert those double floating point coefficients to fixed point. I mean, that's pretty basic. You just need a frequency. We are doing the frequency response. Okay, yes. So if you look at the frequency response, it is pretty much the same as for the unquantized coefficients. I've gone. I've finalized the 16 and 12 after a bit of iterations, because if I reduce to 16 12 to, like, suppose 9 4, and then I run this, uh, look at that. It doesn't serve the purpose, so I have to, like, this is the least I could go. Beyond that, the quality of the filter compromises, and we don't want that. We don't want our coefficients to be large, I agree, but at the same time we don't want our filter response to be not useful. So yeah, this is what we are going with finally. Okay, that's being done. And quantization, what is the coefficients after quantization? So after coefficients are quantized, you can see the number of bits are limited to 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, yep. So let's go ahead and see the filter response. And so YF quant is the signal after being filtered with the quantized coefficient filter. So let's analyze that signal also. Have I used this spec recently? Yes. So yep, quant. Okay, yeah. So pretty much the same response. No component of 1 kilohertz, no component of 5 kilohertz, and we can hear it as well. Arsh, 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 so as you can see, no T sound of the noise. Arsh, arsh. Okay, so now we move to simulating. I'm not gonna make everything real time because it just increased the length of the video, but I'll explain the process in detail. So uh, it's the same filter. I'm using the same quantized coefficient from there, and I'm converting the double signal to a fixed point numbers. 16 bits word length complete. Out of those, 12 are reserved for a fractional part, and then the scope signal from the workspace. It's my rough RST that signal, and then it's converted to fixed point, and that signal is going to the workspace also, so that we can analyze that signal in the workspace by using our spec function and playing it in the MATLAB. Okay, so after that, what we do is we go to one of these an HDL coder and generate HDL code for it. And after you guys have generated an HDL code for it, I need to open the folder. So this folder you will get after you generate the HDL coder. It has a traceability report, and this is the file. Yeah, that's the .v file of the filter. Yeah. So I mean, it has like what are the inputs? So this has one module, notch filter HDL, and inputs as clock, reset, and outputs as X and Y. So it is 230 lines of Verilog code. Imagine writing it by yourself. Okay. So the next part is, what is this? What is this block? FIL. FIL stand for FPGA in loop. So we always have the .v file. We can open Xilinx Vivado and create a .bit file and run on our FPGA. But for that, we have to have some memory in which I save my audio file, and then I have to interface it with a speaker for output. But We can avoid all of that by using this technique called FPGA in loop. It takes in the real-time signal. It takes in real-time signal from the workspace of the MATLAB, or yeah, from anywhere. It just takes the signal and then gives the output to the MATLAB, and then again this loop kind of continues, and we prototype the real hardware of FPGA as a block that's presented here. So how it's done, how this block comes here. So for that I need to show you something. I mean, there is the extensive MATLAB documentation that I've gone through. I can share the links in the description. So this is where you select your FPGA board. I'm working on this board, and you can add your like the .v file that I've showed you. This same .v file you can add over here, make it a top file because that's the only file we are using. These are input output, and then after that you can click on sign, and then we extend the fractional part to 12 bits, and then you can click on build. I've already built I've done all that process. I'm not going to repeat it again, and for that I have received this, I have this .bit file. So I have loaded, I need just to load this .bit file, and after all that process you will have another folder called, yeah, notch filter hdl.fil. File stand for FPGA in the loop. So I have a bit file over here. That same bit file has to be loaded in this. So you see a lot of snake-like LEDs on my FPGA. It's a default program that runs on it, and let's run our simulation, and throws in an error, did not receive. Okay, let me load the bit file. Okay, so I mean every time you open this model, you have to load the your .bit file in this FPGA. So I mean it's pretty obvious because like uh, how will it know what's the how will it know your logic then that's described in your HDL? And while it's being done, I can share some documentation from MATLAB that can be pretty handy. And these are all the steps that I haven't explained in the details. These are all logistics. I should have, because it can save you guys time from troubleshooting. So as you see that the default program is not displayed on it, and FPGA program file loaded successfully. So that means that that our .bit file is loaded in here successfully. Click on apply, click on OK, and then run our simulation. It should run this time. It's running. You can see the output, and so yeah, as you see that, I mean, if it was for, I mean, this is happening real time. This is me saying Earth. This is me saying Earth. This is me saying Earth. So, so while this, after this will be done, what we will be having is we'll be having our the filtered signals from the FPGA, which will be saved in YFPGA variable in the workspace. We are going to go to the workspace and then analyze and compare it with our original signal and see. It's almost done. I'm using Xilinx Vivado 202 Platinum with my MATLAB for HDL synthesis. Uh, okay. Okay. Oh, yep, I have it. I have YFPGA. Let me analyze now. Spec Y. So in order to use this function, I have to again convert those fixed point numbers to double floating point numbers. What is the name? Out dot YFPGA. Yes. Let us see the response. Oh, use parentheses. I might, and then it's too many arguments. I might have missed something here. Just wait a minute. I mean, sometime I was just using too many parentheses, sometimes too less. So yes, no component of 1 kilohertz and 5 kilohertz. Let's play it. Arsh, 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 arsh. So that's how we implement a band stop filter, notch filter in an FPGA by using hardware in loop method or FPGA in loop method. Thank you for watching the video. In case you have any questions or queries or you are stuck troubleshooting, please let me know in the comments.